Okay, on to part C. Part C asks for the amount of energy accounted for in the first 5 coefficients in the fifth degree Fourier polynomial. So we need the first 5 coefficients and the constant term, which we found earlier, in order to figure out how much energy is accounted for. All right. What I've done here is written up the coefficients as a sequence, and I've defined them as a function because I'm going to use them later to build the polynomial. So I defined it as a function of m, and then what it's going to do is going to let p go from 1 to 5. And so here are my first 1, 2, 3, 4, 5 coefficients. Right? Now I've also defined this as a function of m so that I can recall those later, and I'll point it out where I use those. The b's, we already know they're going to come out to be 0, so we just verify that. And so our fifth degree polynomial is going to look like this. So I have to add in the constant term separately, but because I saved my a's as a function of k and my b's as a function of k, I can actually just use the sum command to write out the rest. That's going to be really nice if we have a larger degree Fourier polynomial we need to find. Which is what we're going to do next, because this isn't in the book, but according to the book it takes 13 harmonics to get 90% of the energy. So let's find the first 13 coefficients. So basically the exact same code, except now we're going up to 13 instead of just to 5. So there's our first 13 coefficients. Alright. Now we're going to find the total amount of energy accounted for in the 13. Alright. We see that we do in fact get 90%. Now we didn't look at the percentage from the fifth degree Fourier polynomial, so let's go back and do that. So it's the exact same code, just k is going from 1 to 5. It's really nice to use the sum command, which was the advantage of putting in the coefficients as a function of k. So we see that a fifth degree Fourier polynomial is only going to account for about 61.5% of the energy. Right? We can actually use this as a measure of accuracy, and we'll see that later in the plots. So then our 13th degree polynomial is going to look like this. Same code as finding the 5th degree polynomial, except now I can expand k to be 13. So take advantage of that sum command. It will really save you some time. Now we're going to be looking at the plots in the next part. So what I'm going to do is I'm going to store the 5th degree polynomial. I'm going to call it D5 and color it blue, and the 13th degree polynomial. Right? So let's go ahead and look at our plots together. So df is the plot I stored for the original function. D5 is our 5th degree polynomial. We can see it's not a really good representation of this particular pulse train. It's because the pulse train is so narrow, it's having a really hard time being able to account for a lot of the energy. Now if we do it with our 13th degree polynomial, we see we do get a better representation. And notice, remember, we only did this from negative pi to pi, but this graph is from negative 3 pi to 3 pi. So the fact that the Fourier polynomial is periodic takes care of that. We only need to focus on one period, which is one of the great things about Fourier polynomials. Here we go, we'll look at a plot of all 3 of them together. All right, we can see that the 13th degree is a much better approximation. What we saw is that the 13th degree accounted for 90% of the energy, where the 5th degree, this blue one, only accounted for 61.5% of the energy. If we were to do a higher degree, we would get a larger percent of the energy. There will be a copy of this code on the website as well, so feel free to take it and modify it however you need it.